to Physics for Everyone classes. This is your Satish. So in this video, we can see about simple microscope. So where to use this instrument, the simple microscope? That's the first thing. So whenever we want to see the objects in the bigger way, in the magnified version, up to certain limit, there we can use the simple microscope. You should have some limitations. Up to some extent only we can magnify the given object. So more than that, it's not possible because already we have got human eye. There is a limitation for the power of accommodation. So there inside our eye we have got eye lens. It has got its own power of accommodation. There we can see the object which is closer to us as well as which is very far from us. So what would be the near point for the normal person? Yes, it is 25 centimeters, which is called as least distance of distant vision. And the far point is up to infinity. It means for a person, for an adult person, the average distance to see the object very clearly, it has got two limits. Where to where? From 25 centimeters to infinity. Wherever you keep the object, we can see the object very clearly. But when we take the object which comes under 25 centimeters, there is a limitation. We cannot see the object distantly or clearly. Because of that limitation, the simple microscope which is being used to magnify the size of the object. And we have got our limitation. With the help of the instruments, we can extend up to some level. We can see the magnified version of the given object. Let us see how. So before taking this one, we need to know a bit about visual angle. So let us see, if I take this object very closer to me, in the sense which is more than 25 centimeters. If I keep here, approximately it is 30 centimeters. So I feel that this much is the size of the object. What I got the feeling? Okay, this much is the length. If I take this object away from me, now I am feeling the size of the object is a bit smaller, but really the height of the pen does not change. So what changes here is the angle subtended by this object on the eye gradually decreases when this object is taken away. Now let us see the same thing diagrammatically. So here is the object has a height h. H is the height of the object which is placed at a point A. Now this object subtends an angle, how much here? Theta A at the naked eye. There you can see the angle subtended by this object at the naked eye is theta A. Angle subtended means that the light rays which are coming from the object falling on the eye with how much angle? Theta A. That angle is called as a visual angle. Now the same object of the same height is taken away from the eye. There you can see the light rays which are coming from the object, one from the top and other from the bottom. Now these light rays are making an angle theta B, which is lesser as compared to the earlier angle. So depending on this angle, the image which is formed inside the eye, where on the retina, there it changes. If more is the angle, more will be the height of the image on the retina. If lesser is the visual angle, lesser will be the height of the image on the retina. So that we perceive the height of the object changes, but really there will be no linear magnification of the object along its lengthwise. There is no change. The magnification here is done with the angular wise. That's why it is called as an angular magnification. We should call it as angular magnification. Right. So visual angle means, you can write what is visual angle. It is the angle subtended by the object on the eye is called as visual angle. Say the angle subtended by the object on the eye is called as a visual angle. If more is the angle, if more is the visual angle, we feel that the height of the object is more. If less is the visual angle, we feel that the height of the object is smaller. So we all experienced when we see the flight which is going very far from us, there are some 1,000 kilometers away from us, we feel that the size of the plane, aeroplane is very smaller. But actually, it has got a bigger dimensions when we see from the near distance. So it is all about the visual angle. Depending on that, we are feeling the size of the object is bigger or smaller, but actually there is no change in the linear magnification. So we got the visual angle. The next part is that, as I told, when we take the same object which is very closer to the eye, I'm feeling now the size of the object is increasing. Is it okay? If I'm taking which is less than 25 centimeters, we will get bigger in size, but there will be a loss in the clarity. We are not seeing it distinctly or clearly when the object is taking under 25 centimeters. Because of the limitation, as I told you earlier, that the near point distance is 25 and far point distance is infinity. Depending on the size of the object, we can see, I can see the sun from here, which is a very far distance from here, because as the size is bigger, I'm seeing it. If I take this pen to that distance, can I see this one? No, it is not possible, because the light rays are not captured from the distance to the eye. That is the reason. So where we are taking the object which is less than 25 centimeters, there I feel that object is there, it has got some dimensions, but I'm not seeing it clearly. So there will be a limitation. Now what we have to do? So we need to take the help of some instrument. Now it is called as the simple microscope. How does it work? Let us see. So here I'm taking the same object. You can see what object I am taking here. The same object is taking of a height h and one convex lens, which is itself is a simple microscope and magnifying glass. This is the convex lens. Now take this object under the focal length of this lens. You can see the convex lens has got its own focal length on both the sides. So the distance from optic center to focus is called as its focal length. Now the object is taking within the focal length of convex lens, and the distance is not mentioned, so let it be taken as UE. UE is the object distance. Now draw two lines. The one line is parallel to principal axis and the second one is passing through the optic center. If any ray passing through principal axis after passing through the lens, there the light ray should pass through its focus. There you can see, after refraction through the lens, the light ray is passing through the focus, and the ray which is passing through optic center without any deviation, it will travel in straight line, and you feel that these two light rays are divergent, and we cannot get the image when you extend in the forward direction. What should we do to get the image? So we are extending these divergent light rays in the backward direction. Somewhere these two rays will meet, appear to meet, and there you will get the final image of this object. So here you can see the height of the image is named as h dash, which is very bigger as compared to the h. As you have studied the cases of convex lens, there it comes as the last case, sixth case, when the object is taking between optic center and the focus, and the nature of the image is virtual, erect, and magnified. So in this way we are magnifying the size of the object before the light rays are really entering onto the eye. And this eye is not feeling the light rays are coming from here. This eye is feeling the image formed by this convex lens acts as an object for the eye. And we are naming the distance from this image to the lens. The optic center of the lens is called as image distance. Let it be taken V. And this V distance we can change by changing the position of the object. From where to where? So we can change this V from least distance to the infinity by changing the object distance. So there it comes as two cases. One, the final image which is formed at least distance of distant vision, because the eye has got its own limitation. Accordingly, we need to adjust. What is the limitation of the eye? If any object or the image formed by this convex lens must be in between 25 centimeters to the infinity, and we are trying now. So what we are trying, the image formed by this object due to this convex lens is formed at a distance V, and we are making this distance V either at least distance of distant vision or at the infinity. So let us take the first case, case 1, that is image. The final image is formed at least distance of distant vision, which is 25 centimeters, or is denoted by capital D. Now you can see here the distance, how much I am taking here. Here you can take V, capital V is equal to how much? D, because we are adjusting the image position by changing the object distance in between optic center and the focus. Now, by using lens formula, we can find the object distance. Before that, so with the use of simple microscope, what we are trying to find? We are finding the magnification, angular magnification, which means the height of this image which is formed by this convex lens, how many times it is bigger than the height of this object which is kept at least distance of distant vision. Suppose if I am taking the position A to the eye distance, I am taking it as capital D. There only you will feel that this height is maximum, and there you got the angular magnification. How much? It is nothing but the visual angle. We are not comparing anything there. Directly you can write the visual angle here is theta naught is equal to height of the object divided by the distance you can take here. The distance is how much? Least distance of distant vision, h by d. Because the angles made by the object at the eye is very smaller. If the angle is small, there you can take the tan theta. Tan theta is equal to opposite side divided by the adjacent side. Opposite side is how much? H. Adjacent side is D, where D is the least distance of distant vision. So h by D, which is equal to theta naught, where it is named as the visual angle. The maximum angle which is subtended by the given object at the eye is called as visual angle. There we get the maximum value. More than this you cannot get without using any instrument. So here what we are trying, we are increasing the visual angle by using the convex lens. Now how much is the visual angle here with the help of the convex lens. Now, the angle made by this image, you can see the angle made by this image at the naked eye, which is called as visual angle here. How much it could be? Let it be taken as theta. Earlier I am taking it as theta naught without instrument, and with the instrument I am taking visual angle as theta. And there you can write how much the visual angle here is. Theta is equal to tan theta is equal to, there you can take in two ways. Tan theta is equal to opposite side divided by adjacent side. If you take the bigger triangle here, right angle triangle, so theta is equal to h dash divided by adjacent side is how much? V, which is equal to, or else I can write from the smaller triangle tan theta is equal to h divided by UE, h divided by UE. And you can take this is the equation 1 and here is the equation 2. What is theta naught? Visual angle without simple microscope, without convex lens. Theta is the visual angle for the same object with the help of the instrument. There you can write theta is equal to h dash by v is equal to h by UE. And if you divide these two to get the magnifying power, angular magnification, which is equal to theta upon theta naught. So we are finding how many times the size of the object increases in the form of the image compared to the size of the object there without the instrument, which is called as the magnifying power. With respect to means, with respect to what? With respect to the size of the object without instrument to the size of the image with the instrument, with the convex lens, which is called as a magnifying power, theta by theta naught. And that is equal to, what we can write theta? I can write it as h divided by UE. Out of these two, I can take one, h by UE, and divided by theta naught is h by d. I can write it as h by d, and that is equal to h get cancelled. You will get d divided by UE. So what is UE there? It is the position of the object which is in between focus and optic center, which is unknown value. We need to find that. By taking the image, we are fixing the one position is at infinity, one position is at least distance of distant vision, and the other position is at infinity. Is it okay? So we got the magnifying power is equal to d by UE, and you take this case, the image is formed at least distance of distant vision 25 centimeters or at d, and the position of the image is being fixed here, v is equal to d, to get which value? In order to get the UE value. So up to here, okay? So let us move forward to find the UE, position of the object, by fixing the image distances at least distance of distant vision. Right. Now tell me, what's the lens formula? We know 1 by v minus 1 by u is equal to 1 by f. It is the lens formula. 1 by v. And we are talking about the case where the image is fixed at least distance. There you will get v is equal to d. And according to sign convention, where d, you can see any distance should be measured from the optic center to that image or the object or the focus. Always you should count the distance from the optic center. If that measurement is opposite to the incident ray, you can see the incident ray is towards right, the light rays are traveling towards right, and the measurement is taken towards left, that measurement should be taken as negative. So V should be equal to minus T. And what is the U? U, we need to find the value. Let it be taken as U or some other variable. So better you take U as U only. You will get the answer with sign convention at last. And what about the focal length? Focal length is positive because we are looking this focus. The image will be formed on the other side. The first focus we can name it as. And you should take that reference. So for the convex lens, the focal length should be taken as the positive. Focal length is positive. And substitute the values here to find the position of the object. So 1 by minus d, where v is minus d, minus 1 by u, which is unknown value, and it will be taken here. ue, some name I was given, ue, and which is equal to 1 by f. From here you will get 1 by ue, which is equal to, if it goes there, this will come this side, 1 by minus d minus 1 by f. With that, 1 by ue is equal to, minus is taken common outside, and df is the LCM. You will get f plus d. So 1 by ue is equal to negative of f focal length plus d least distance of distribution divided by d into f. And take this value directly there in this expression to find the magnifying power. Therefore, magnification, angular magnification or magnifying power is equal to, of the convex lens, is equal to d into, you can replace 1 by u directly because here 1 by u is there, here also 1 by u, and don't take this negative sign here because we are not taking the sign with u. U is also on the left side. We got in the answer. That's the proof. We got the negative answer sense that the object is on the left side. It take only the value. So ue, 1 by ue is equal to f plus d divided by d into f. Here d get cancelled, which is equal to 1 plus d by f. So the most important expression for the magnifying power of the simple microscope, there in the case when the final image is formed at 25 centimeters or least distance of distribution. You got the one result. So please remember, for the first case, magnifying power is equal to 1 plus d by f. While we are dealing the numericals, there you can see d is fixed 25. If it is given or not given, for the person, average distance to see the object clearly is 25 centimeters. If I give the focal length of the convex lens, directly you will get the magnifying power. In this way, we can get the, so how much the convex lens enlarges the size of the object in the angular wise, we can calculate it. And what is the second case? The second case is that we are adjusting the image should be formed at infinity. So once the image is formed at infinity, there we know this object distance, the position of the object should be at the focus. And there it comes, and this distance is being fixed. How much it comes now? When the object distance is equal to the focal length, the final image formed by the convex lens should be at infinity. Let us see that. And the second case is the image is adjusted at infinity by changing the position of the object. Now the image is formed at infinity. The image is formed at infinity. And for this, again, we need to take the lens formula, which is 1 by v minus 1 by u is equal to 1 by f. Now what is v? V is adjusted to infinity. Either you can take plus or minus, doesn't matter. 1 by minus infinity minus 1 by u, which is equal to 1 by f. 1 by infinity value comes it as 0, and there u is equal to how much you will get? Minus f. The object distance comes as how much? Negative of the focal length. Don't take this negative sign there while we are dealing the numerical value of object distance. Directly you can substitute f only. The negative reflects the sign convention. It's the proof that the object is on the left side of the convex lens. Now, magnifying power of simple microscope is equal to how much it is? Earlier I was given that as it is d divided by u, d by u, which is equal to d divided by how much you got here? Focal length directly, d by f. So we got the result here in this case, the magnifying power is just d by f. And by comparing the two expressions, the record earlier case, magnifying power when it is at least distance of distant vision, how much you got? It is 1 plus d by f. And magnifying power when the image which is existed at infinity, the far point d by f. By comparing these two values, it is clear that this magnification is smaller as compared to this one by 1 unit, or this one is more as compared to this one how much by 1 unit. And which one is which one we are choosing, it all depends on that. Do you want a bigger one? Yes, you want a bigger magnification, angular magnification of the simple microscope, we can go with this one. But at the same time, we need to pay something that the ciliary muscles which are there inside the eye is most strained. And here the magnification is somewhat smaller. Magnification is there, angular magnification is there. But here the eyes are most relaxed state. There we can see the object very clearly. So which one we are choosing, it all depends on us. When we are seeing the mountains or the scenery which are very far from us, we can enjoy the sightseeing for hours and hours and hours. And if I'm asking to read the book for 1 hour or 2 hours, generally, you will get bored with the subject also sometimes. At the same point of time, if you are reading the book for hours and hours, because the letters which are closer to you, maybe under 25 centimeters or 30 centimeters, the eyes are get strained because you are focusing at the point where the object is closer to you. The same reason there, if you are looking the object which is closer to you, that is at a 25 centimeters, the magnification is bigger, but the eye is very much strained. Where you are looking the same object which is very far from us, there the eyes are most relaxed state. But in the both the cases, compared to the earlier case without instrument, there we got the angular magnification with the help of the simple microscope. That's it about. And the next section we can see about the compound microscope. Thank you.